Chromatography is a physical method of separation. It is based on the distribution of the components of a sample mixture between two phases. One phase is stationary, the other mobile. It percolates through the interstices or over the surface of the fixed stationary phase. The components of the sample are carried by the mobile phase. As they move through the stationary phase, they distribute themselves between the two phases, with each component spending a certain fraction of time in each phase. If a component spends only a short time in the stationary phase, it is carried more rapidly through the column. Another component may spend more time in the stationary phase, thus moving more slowly and emerging later. It is this ability of the stationary phase to hold the components at various degrees that results in chromatography's great separating power. As each component emerges, it is detected, and its presence is recorded in the form of a chromatogram. The order in which the peaks appear on the chromatogram provides the data from which the components may be individually identified, while the heights and areas of the peaks permit the determination of the amounts of the individual components present. This complex separation process is called elution. It is the most common method in chromatography. The mobile phase may be either gaseous or liquid. Where the mobile phase is a gas, the technique is called gas chromatography. Where the mobile phase is a liquid, it's liquid chromatography. The stationary phase may be either liquid or solid. The combinations of these give us the four types of chromatography: gas-liquid, gas-solid, liquid-solid, and liquid-liquid. Columns are used in all four types of chromatography. If the stationary phase is a solid material, its particles are packed into the column. If the stationary phase is a liquid, it is first coated over solid particles of an inert material that supports the liquid stationary phase. The mobile phase, flowing through the column, carries the components of the sample. Chromatography may also be performed by setting up the stationary phase on a plane surface and flowing the sample-carrying mobile phase over it. Paper chromatography and thin layer chromatography are variants of plane chromatography. The actual separation process is accomplished by partition, or differential solubility, by adsorption, or by separation according to the sizes of the molecules, as in gel permeation chromatography. Ion exchange chromatography is a special type of adsorption that utilizes electrovalent bonding. In some cases, the separation process may be a combination of these techniques. Let's look more closely at each type, beginning with partition chromatography. For simplification, we'll show the column in this way, with the mobile phase as the upper layer and the stationary phase, a liquid in this case, as the lower one. We'll divide the column into a series of identical segments and assume that within each segment an equilibrium distribution is achieved during the passage of the moving phase. Each segment is called a theoretical plate. If we introduce a sample that consists of just one component, its molecules are immediately distributed between the two phases and reach a state of equilibrium, with a certain concentration in the mobile phase and another concentration in the stationary phase. Their ratio is known as the partition coefficient K. Its value depends on the sample and the stationary phase, and also upon the working temperature. Now let us take a sample that is a mixture of two components. In the column, the components distribute themselves according to their partition coefficients. In the mobile phase, in this particular case, there are half as many red molecules at equilibrium as in the stationary phase. With the second component, the blue molecules, the opposite is true. There are twice as many in the mobile as in the stationary phase. Now let's move the mobile phase to the next step, or plate. Equilibrium will be established in both plates, and the same ratios will hold for the distribution of the molecules of each component. This is constant under identical chromatographic conditions. We continue to move the mobile phase along, simulating in this step manner the flowing stream. With the blue component moving more rapidly than the red, the separation becomes successively greater. If we go on for many more plates, the blue will eventually be completely separated from the red. Besides the flow rate of the mobile phase, the components' travel through the column is determined by their partition coefficients. Thus, the ratio of the K's, designated alpha, characterizes their separation. Alpha is called the separation factor, or the relative retention. Its value depends on the two partition coefficients, and thus on the stationary phase and the working temperature. The separation factor can be increased by proper selection of the stationary phase. However, a large separation factor does not of itself assure good separation, because diffusion of the bands as they pass through the column may cause overlapping and thus reduce the separation. The greater the number of equilibrium steps, theoretical plates, the greater the separation or resolution. Increasing the length of the column will increase the number of theoretical plates. We'll assume that we have a certain column length, distance between peaks, and resolution. The distance between the two peaks is directly proportional to the column length. But the band width, and therefore the resolution, is proportional to the square root of the column length. Thus, doubling the column length and the distance between the two peaks will only increase the resolution by the square root of 2, or 1.4. The number of theoretical plates can also be increased by making a better column, one having more plates for the same length. Obviously, this is the better solution. Partition is the basis of separation in gas-liquid, liquid-liquid, and paper chromatography. Now let us examine the adsorption process, which is the basis of separation in gas-solid, liquid-solid, and thin-layer chromatography. Adsorption is a surface phenomenon. Gases and liquids are concentrated at the surface of a solid. Molecules of the sample are in equilibrium between the stationary solid surface and the mobile phase. If one component, such as the red molecules, has a high affinity for the solid, it moves more slowly. Sometimes binding may be so strong that there is no movement at all. This is irreversible adsorption. In this case, the adsorbed molecules may be removed only by high temperature or displacement by a more active substance, the basic principle of displacement chromatography. The chromatographic techniques can also be divided according to the nature of the mobile phase. The most popular technique is gas chromatography, abbreviated as GC. Today, over 80,000 units are in use worldwide. The popularity of GC is due primarily to its simplicity, great resolving power, and sensitivity. Let us examine the parts of a gas chromatograph and understand why it works so well. A high-pressure cylinder supplies the carrier gas, the mobile phase. It flows through a pressure or flow regulator and into an injection block, A syringe or a sampling valve is used to introduce the sample into the carrier gas stream. If it is a liquid, it evaporates instantaneously. The carrier gas carries the sample vapor through the column, where it is separated into individual components. As each component leaves the column, it enters the detector, which responds by sending an electrical signal to the recorder. The recorder traces a peak for each component. The effluent from the detector is usually vented to the atmosphere. The injection port, the column, the detector, and all the connecting lines are heated to avoid condensation of the sample. The column is heated to provide a reasonable partitioning between the two phases. The carrier gas should be pure and chemically inert with respect to the sample. High-density gases give slightly better column efficiency, while lighter gases provide speedier analyses. But the choice is usually determined by detector requirements. The most commonly used gases are helium, nitrogen, argon, and hydrogen. The sample requirement of a gas chromatograph is very small. For a liquid sample, about a microliter or less. It is easily and reproducibly handled with a syringe. Solid samples are best dissolved in a volatile solvent and the solution injected into the carrier gas. The sample volume of a gas is usually less than 5 cc's, readily handled by the larger syringes. For more accurate injections, gas or liquid sampling valves are available. The column is the heart of a gas chromatograph, and choosing the proper one is very important. There are two basic types, packed and open tubular. The shape of the column is determined by the geometry of the column oven. Coiled columns permit the use of small ovens. If a U-shaped column is preferred, the instrument requires a larger oven. Typically, packed columns are made of copper, stainless steel, aluminum, or glass, which is preferred for its inertness toward unstable samples. A packed column is filled tightly with solid, porous particles of uniform size. In gas-solid chromatography, the packing may be an adsorbent, such as silica gel. In gas-liquid partition chromatography, the packing usually consists of diatomaceous earth or other support particles coated with the stationary phase. For example, 20% carbo wax. Porous polymer resins represent a special type of column packings. The materials are tightly packed into the column. Open tubular columns are not packed. Their inside diameter is only 1/2 millimeter or less. They are coated inside with a thin film of stationary phase and run up to several hundred feet in length. This chromatogram shows the very high efficiency of open tubular columns. Over 120 peaks were resolved in 45 minutes. Because choosing the proper stationary phase is so important in partition chromatography, let us investigate the factors that influence the selection. The choice of the stationary phase depends on the chemical nature of the sample and its boiling point. It is important that the stationary phases have very low vapor pressure at the working temperature. For most of the samples analyzed in practice, one can select among stationary phases with widely different chemical natures. The basic selection rule is, like dissolves like. Thus, if possible, one should select a stationary phase having functional groups or polarity similar to those of the sample components. Hydrocarbons are best analyzed on hydrocarbon-type stationary phases. For the analysis of esters, polyester-type stationary phases are used. And for alcohols, aldehydes, and such, polyglycols have found the widest application. One can make a list of stationary phases and sample components by decreasing polarity. Alcohols, ketones, and aldehydes are very polar due to dipole moments or hydrogen bonding. The greater the polarity of the stationary phase, the greater is the retention of a polar solute relative to that of a nonpolar solute with similar boiling point. This can be shown if we analyze, for example, a mixture of ethyl alcohol, benzene, and cyclohexane, each having a boiling point close to 80 degrees centigrade, on 3 different stationary phases of different polarity. The first phase is squalane, a hydrocarbon that is nonpolar. Therefore, it retains the nonpolar cyclohexane the longest, while the strongly polar ethyl alcohol emerges first. Phenylsilicone oil, the second stationary phase, is moderately polar and contains aromatic groups. Accordingly, the retention time of benzene is longer than the retention time of the nonpolar aliphatic cyclohexane. Finally, when using a very polar polyethylene glycol stationary phase, the nonpolar cyclohexane will emerge first, and the polar ethyl alcohol will be retained the longest. The proper selection among the large number of available stationary phases is the key to successful separation in gas chromatography. Detectors measure the concentrations of sample components eluted from the column. The most generally used type does this by sensing changes in the thermal conductivity of the effluent from the column. In such a thermal conductivity detector, the stainless steel block, which is held at constant temperature, has 2 separate gas passages, one the sensing side, the other the reference side. The effluent from the column passes over an electrically heated filament. The flowing gas conducts heat from the hot filament to the cooler metal block at a constant rate, as long as the column effluent consists only of pure carrier gas. Thus, the filament's electrical resistance remains constant under these conditions. Pure carrier gas is always flowing through the reference side. The 2 filaments are incorporated in a Wheatstone bridge connected to a recorder. As long as pure carrier gas is coming out from the column, the bridge is in balance, and the recorder traces a flat baseline. But when a sample component enters the detector, the situation changes. The vapor of this component has a thermal conductivity that is different, usually lower, than that of the carrier gas. Thus, the heat dissipation from the filament suddenly changes. As a result, the temperature of the filament increases during passage of the sample component. This increases its resistance and upsets the balance of the Wheatstone bridge circuit. The off-balance is recorded on the chart paper in the form of a peak. After the sample component has passed the detector cell and pure carrier gas is again flowing from the column, the bridge regains its balance and the pen returns to the baseline. The same thing happens each time the carrier gas brings another component into the detector cell. The advantages of a thermal conductivity cell are that it responds to all sample components, is non-destructive, and easy to operate. Its major limitation is its moderate sensitivity. A far more sensitive detector is the flame ionization detector. It can easily measure very small amounts of a component in small sample volumes. Its construction is very simple. The column effluent is mixed with hydrogen and burned in an environment of air. The conductivity of the flame is measured between 2 electrodes, one of which is usually the jet itself. When only pure carrier gas is coming from the column, the ion current through the flame is very small. When the vapor of an organic substance enters the detector jet, it burns and ionization takes place. As a result, the ion current increases significantly. This ion current is amplified by an electrometer and recorded on the chromatogram. The flame ionization detector does not respond to inorganic substances, including water and air. It is very sensitive and quite stable. The result of the analysis is the chromatogram. Let us see how it can be interpreted and used to identify and quantitate the components of a sample. Each peak corresponds to a component separated in the column. The peak takes the familiar bell shape of a Gaussian distribution curve, if the conditions were selected correctly. In case of insufficient separation in the column, one peak may correspond to 2 or even more sample components. The time from the point of injection of the sample to the peak maximum is known as the retention time, TR. Part of it is the gas holdup time, TA, the time required for the carrier gas to move through the column. It is easily determined by measuring the time from sample injection to the peak of a component like air, which is not retained by the stationary phase, but stays always in the moving gas. The additional time is T'R, the adjusted retention time. It characterizes the retention of the sample by the stationary phase. The retention time is reproducible if the same column is used, together with the same flow rate and column temperature. However, relative retention times must be used for identification when samples are analyzed in different laboratories, because columns and conditions are almost never the same. The relative retention time, alpha, is the ratio of the adjusted retention time of the sample and the adjusted retention time of a standard substance. Because these values represent the time spent in the stationary phase, they are a direct function of the partition coefficient, and therefore alpha is the ratio of the two partition coefficients. The standard is usually added to the sample, and thus both are analyzed in one run. If components have identical or very similar partition coefficients, peaks may be difficult to identify from relative retention data. For absolute identification, the substance emerging from the column should be trapped and transferred to another analytical instrument. For example, an infrared spectrophotometer or a mass spectrometer. The chromatogram also permits us to evaluate the goodness of the column. The retention time and the peak width at base can be used to calculate the number of theoretical plates according to the formula N equals 16 times TR over WB squared. The base width is the part of the baseline cut out by the two tangents to the inflection points of the bell-shaped curve. Generally speaking, the higher the number of theoretical plates, the better the column. Naturally, the number of theoretical plates depends on the length of the column. For comparison of the efficiencies of columns of different lengths, the height equivalent to one theoretical plate, HETP, is used. It is the length of the column divided by the number of plates. The HETP is that column length necessary for equilibrium to be established. Now let us see how the chromatogram indicates the amount of sample components present. The area of each peak is proportional to the amount of that particular component. The quantity for a given component will produce a peak of a certain area, and twice the quantity will produce a peak with twice the area. However, since the detector does not respond identically to equal amounts of different substances, equal areas of two substances do not mean equal concentrations. If accurate quantitative results are required, individual calibration factors must be used for each peak. These calibration factors depend on the type of detector used. In summation, chromatography is a separation technique. It has the ability to perform difficult separations in a relatively short time. It is based on the movement of the components of a sample with a mobile phase over a stationary phase. Each component has a different distribution coefficient between the two phases. As a result, they are retarded by the stationary phase for shorter or longer times, and thus emerge at different times. The relative velocity of a substance is a characteristic value which can be used for identification. Based on the height or areas of the individual peaks after proper calibration, the amount of the sample components can also be established. Depending on the choice of the moving and the stationary phases and the form of the system, many chromatographic methods exist. Among these, gas chromatography provides the best possibility among all analytical techniques for the separation and analysis of complex volatile mixtures. It is rapid, but is restricted to substances that show some volatility up to 300 degrees centigrade. For substances that have high molecular weight or are temperature sensitive, some other forms of chromatography are recommended. In these, the moving phase is not a gas, but a liquid. These techniques will be discussed in the second part of this film.